So it's always a pleasure to visit this wonderful department and at the center of the world. So as Aditi mentioned, I don't live at the center of the world. My topic today, as Aditi mentioned, is one I've been interested in for a long time, but it's become more interesting recently thanks to some surprising experimental work, initially by Pablo Herrero at MIT. I understand that you've heard from Pablo not so long ago, and also from Philip Kim on this topic. So I could have chosen something else, but this is actually what I've been doing recently. So you get my perspective on it. The work I'm going to talk about today is, as I said, I've been worked on this topic for a long time, and with a number of people, most at the University of Texas. And what I'm going to talk about today involves mainly work done with Rafi Bistritzer, who's now at the Weizmann Institute in Israel, Fengchen Wu, who's at the University of Maryland, and Mingxi, who's still in Austin. Okay, so my title said Fundamental Physics with a Twist, and the theme of this talk is that it's proven possible to study really basic issues in condensed matter physics by just taking very simple two-dimensional electron systems and twisting them. And so let me first start off saying something about condensed matter physics. First thing about condensed matter physics is we know what the model is. The model is just the same model that you learned in high school for a structure of an atom. It's just quantum mechanics and Coulomb interactions. And so the main thing about quantum condensed matter physics is we know everything about atoms, but once electrons don't belong to individual atoms, things get much more complicated. As you may remember, the energy scale of atomic physics is, let's say, some number of electron volts. The energy scale, which determines most physical properties, is some number of milli-electron volts, and somewhere between those two energy scales, various things happen, including often our ability to understand what happens. So this cartoon shows the important energy scales of electrons and crystals. And electrons, of course, are waves, including in crystals, and the momentum of the wave is related to its wavelength. And so there's an energy scale associated with electrons hopping from site to site, and the dependence of the energy on the phase difference between different sites, which is the momentum, provides an energy scale. It's basically the velocity of these electrons, and this hopping property determines how the energy depends on momentum. And the other main energy scale is associated with the fact that the number of charges on a given atomic site fluctuates, and there's a big energy cost if instantaneously you have the wrong number of energies on an atom. And just this interaction term can make the physics that emerges at the low energies that are related to physical properties be related in non-obvious ways to the atomic physics that you start with. And here's a cartoon. Actually, this is a cartoon from my friend Randy Hewlett at Rice University, who's an AMO experimentalist, and it shows a diagram for the physics of the cartoon I just showed you, electrons hopping on a lattice with short-range repulsive interactions, and some of the physics that occurs in these systems. And this simple model, as most of you know, is thought to be the basic model of cuprate high-temperature superconductors. And people in the AMO cold atom community have been trying for a long time to solve that problem by simply simulating, finding another physical system which has the same properties by doing quantum simulation, if you like. And this is a cartoon shows, from Randy's lab, shows what they hope to see. They hope to see insulating states. In fact, they've more or less seen that in half-filled. This occurs when the number of electrons per atomic site is 1, let's say. You can have antiferromagnetic insulating states. But what people really want to understand is superconductivity, which occurs close to insulating states and is thought to be related to the magnetic fluctuations that occur in these insulating states. And so the main message of my talk today is through some serendipity that's maybe typical of science. It turns out that this type of simulation, a simulation of strongly correlated electrons in 2 dimensions, is actually possible to do in these Moiré superlattices that I'm going to talk about. So let me first say something about what's a Moiré pattern. I think you all know what's a Moiré pattern. Moiré patterns emerge when you have two-dimensional meshes, two-dimensional lattices, let's say. In this illustration, I have a honeycomb lattice, a two-dimensional honeycomb lattice with gray links between the sites on the lattice. And so if you have 2 of these lattices and you have some slight difference between them, then the way a pattern emerges, a long wavelength pattern emerges from the slow changes in space of how the 2 meshes are related to each other. So for these honeycomb lattices, there's actually a black honeycomb lattice underneath here, which you can't see. But if I rotate it slightly, then you can see as a function of rotation, a pattern emerges that can have a long wavelength if there's only a small twist relative to perfect stacking. And it's exactly those Moiré superlattices like that that have turned out to have extremely interesting electronic properties. Whoops. Okay, so my talk has 2 parts, and please interrupt me at any stage. I promise that I'll stop on time, whether I've finished or not. First part of my talk is I'm going to just say a few words about what are the types of systems, all based on 2-dimensional materials, 2-dimensional crystals, in which you can explore using the formation of Moiré superlattices to tune electronic properties. And the second part of my talk, I'm going to say a few words about this particular case of Moiré superlattices formed by just taking 2 graphene sheets, two-dimensional crystals of carbon atoms, and twisting them relative to each other. Okay, so the Moiré superlattices that I'm talking about are made from 2-dimensional crystals. Pairs of 2-dimensional crystals, or in general, you might be able to stack more than 2 pairs of 2-dimensional crystals that form a Moiré pattern, either because the 2 crystals have slightly different lattice constants, or because they're twisted relative to each other by a small angle. And the systems, the 2-dimensional crystals that that we have developed a lot of ability to perform physics experiments on, to isolate in nearly perfect form, are 2-dimensional, a sheet of a graphite crystal, a 2-dimensional graphene crystal, Also turns out that if you put graphene on hexagonal boron nitride, which is the 3,5 version of graphene, that introduces some interesting wrinkles. And so they're basically these graphene systems that you can make Moiré superlattices out of. And then there are the next best studied two-dimensional crystal is transition metal dichalcogenides. So these systems, when you make them out of group 6 elements, most of them are semiconductors, fairly large gap semiconductors, and you can make Moiré superlattices out of them. I'm going to mainly just talk about, in my talk, about these semiconducting transition metal dichalcogenide systems and graphene systems, but you can also make Moiré superlattices in two-dimensional crystals that are superconductors, like niobium diselenide, for example, and in magnetic 2D crystals like chromium iodide or other two-dimensional magnetic materials.
What do you mean by flavor?
Yeah. So I'll say what flavor means, but basically the low energy description of these systems, the electrons move through space with a momentum, but for every momentum they can be in one of 2 spin states or in one of 2 valley states. So there are altogether 4 flavors that are possible for each electron. Okay? So I'll say more about that later. Okay. So in these, I'm only going to talk today about the properties of electronic quasiparticles in these Moiré superlattices. But this is a fancier pointer than I understood. There also are bosonic objects that live inside these crystals, collective excitations, either excitons or plasmons, that are also described by models, periodic models with the periodicities of these Moiré patterns. And okay. So let me start with the simplest case, and I'll explain why it's the simplest case in just a moment. Okay. So one idea that I will use is that you can, when you form these Moiré superlattices, locally, you can think of the local change of the system simply as a local translation of one crystal relative to the other. So for example, if I have a fixed blue crystal, honeycomb crystal in back, and I have on top of it a red crystal and rotate it by an angle theta, small angle theta, then near some position, the amount by which a latticite has moved relative to the layer below it is proportional to how far you are from the axis of rotation. And so this pattern is periodic because it's only the translation of one lattice relative to the other modulo the lattice vector of the material underneath that matters. And that displacement of one layer relative to the other modulo the lattice vectors of the material underneath varies slowly in space and produces this periodic pattern. And
is it exactly periodic?
It's not exactly periodic. So in general, if you have two two-dimensional crystals and rotate one relative to the other, you don't end up with a crystal. So if you really keep track not of the what you see here with your eye, which is the variation in space of the local stacking arrangement, but instead keep track of what's going on with every lattice vector, that is not perfectly periodic. Okay. Okay. So let me start with the simplest system, and I'll say why it's the simplest system. So it's in two-dimensional semiconductors. These semiconductors are transition metal dichalcogenides. Those are the two-dimensional semiconductors we know best. For example, tungsten diselenide, molybdenum diselenide. I'm only going to talk about the electronic quasiparticles, and in a certain region of energy. For example, if we're interested in the region of energy near the top of these states below the gap, so-called valence band states of this semiconductor, then these states can exist only in the tungsten layers. So in this system, so it turns out that if you look at a perfect two-dimensional tungsten crystal, there are two places in its momentum space where the valence band reach their maximum energy. And the low energy physics is controlled by the states at the top of the valence band that are occupied by holes, if you put a few holes into the valence band, and they're in this tungsten layer. So, normally for every momentum, you have two spin states, but it turns out this semiconductor doesn't have inversion symmetry, and it has rather strong spin-orbit coupling. So at every momentum, the double degeneracy that you normally associated with spin is lifted. And so the states at the top of the valence band are not spin degenerate. But on the other hand, the way time reversal symmetry appears in this system is there's a state with one in one valley near a momentum where the valence band reaches its maximum, and it has a time reverse partner state which has the opposite momentum. It's in the opposite valley, and it has the opposite spin. So that means that in a perfect tungsten diselenide crystal, there are two states let's say, for every two bands at the top of the valence band. So this is two flavors in the language I was using before. So this is the simplest case. And so here's a, whoops. Have to figure out how to undo that. Okay, yeah. Okay. Yeah. So here's a way to actually estimate to build a model of the electronic properties of these states at the top of the valence band of this hetero bilayer when I form a Moiré superlattice. So if I actually look at how the energy at the top of the valence band varies as I translate a tungsten diselenide layer relative to a molybdenum diselenide layer underneath, you'll find that the bands go up and down in energy. And so, for example, the highest energy occurs, in other words, the most extreme energy in the valence band occurs when the electrons, which actually reside on the transition metals, lie on top of, are right above a selenium, negatively charged selenium ion from the layer below. So very simple to understand how the energy of the electrons on tungsten sites in the tungsten diselenide vary as you move the tungsten diselenide layer over the molybdenum diselenide. Turns out that these energy scales which act like a potential energy for the particle, are some tens of milli-electron volts. And, and that energy, as I was saying before, as a function of the position, the displacement of the tungsten diselenide layer crystal relative to the one underneath, will have the periodicity of the lattice constant underneath. Because if I'm sitting on top of a selenium ion and I move by a lattice constant, I'm still sitting on top of a selenium ion. Okay? And so if I keep track of that effect, then what happens when I have a Moiré superlattice is basically this periodic potential, which has a scale of some tens of milli-electron volts and is keeping track about whether the orbital is sitting on top of a selenium or sitting on top of a tungsten or whatever, just provides a potential energy that whose size is always the same, but which varies on a length scale that I can adjust just by changing the twist angle relative to each other. And what's more, just as part of the properties of these two-dimensional material, the layers are not tightly bound to each other chemically. They're just coupled by van der Waals interaction. They tend to be rather far from each other. And so an electron sitting on one layer of material looking at the other layer doesn't see some sharp change as it moves through space. It's seeing the other layer from far away, and so it sees the other layer as something smooth. And you can see that these potential variations are smooth, and because they're smooth, when you do a Fourier expansion of them in terms of different harmonics of the basic two-dimensional periodicity, only the lowest harmonic plays an important role. And so it turns out that when you put in symmetry, that means that this periodic potential only depends on two parameters: the strength of the potential and on where the potential has its extrema, maxima or minima, and that's more or less determined, fixed. It's the same for all these materials. It's, as I was saying, potential is greatest when the electron is sitting on a negative ion, and so all of these systems are the same. And because there are two states at each momentum, one in each valley, these are far removed regions of momentum space, then this is actually a perfect simulation, if you like, realization of a quantum system that's described exactly by a Hubbard model, by a two-dimensional periodic lattice model. It's actually two-dimensional electrons moving in a sinusoidal potential, lowest harmonic potential, which has actually, it turns out in this case, because the underlying lattices are triangular, the Moiré superlattice potential also has triangular lattice symmetry. And okay, so this is actually from a theoretical point of view, this is the simplest example of a Moiré superlattice system. I can keep track of the effect of the environment as just a function of position, because all of the states I'm interested in are actually localized in the same small region of momentum space where they have an energy at the top of the valence band. And yeah, okay. So let me, so this is this system, if you could actually measure it, and people are maybe not quite there yet in terms of the quality of the materials, although it's definitely coming. you can explore the properties of a two-dimensional system of electrons on a triangular lattice. Turns out that you can get to a region where one band of electrons, one energy versus momentum state, is well isolated from the others at twist angles of 1.5 degrees or so. And these bands, gaps between different bands, have been seen in experiment. So people are making progress on realizing this system.
So to add electrons, you would dope it, or you would put it into some kind of structure where you could put a gate voltage? Is that what you'd have to do?
Yeah, so there are, so the most important lessons are that the Moiré superlattice just gives you a way of making the lattice constant, not the microscopic lattice constant, but making it something that is 100 or times bigger or so, making it 10 nanometers instead of 1 angstrom. And that means, of course, because the lattice constant is humongous, that means that the number of electrons you need to add to fill a band is much smaller. And in fact, you can completely occupy and empty these bands with gates. So you can explore any band filling without changing the chemistry at all, without any chemical doping. Okay.
Does it matter which layer are you putting electrons in? Is it going to be done?
In this case, this is a model for states, the highest energy valence band states, which are localized in the tungsten diselenide. So whether you had it back, no matter where the gate was in the regime where this model applies, it would mainly influence electrons in the tungsten, occupation in the tungsten. Okay.
Can you slide the layers across, or they're like totally stuck to each other? I mean, you're mentioning this kind of van der Waals force, but I mean, experimentally, can you move them against each other, or not really?
So, I haven't said, I took out the slide about how people,
Right.
how my experimental friends actually make these systems, but they start from a two-dimensional crystal,
Right.
tear it in two,
Right.
pick up 1/2,
Set it on a,
twist it by a controlled amount, and try to put it down as flat as they can.
Right.
And it turns out that when you make a Moiré superlattice, if you after you put it down, it kind of gets stuck when you put it down. It's important that it gets stuck because the lowest energy configuration is actually for it to realign.
Right.
Okay, but if you could move it, you would just take. It turns out that just moves this center, moves this Moiré potential.
Right. But there's an interesting thing where, small motions, that pattern moves super fast, like
Yeah.
a phase velocity.
Yeah.
I'm just wondering if you can do anything interesting with that. Because like a
Nobody.
very small motion would make your potential move ridiculously fast, right?
Yeah. There might be some things related to that in terms of how electron-phonon interactions in these systems, but probably won't have time to discuss them. Okay, but that's exactly true. So this system, if one could study the electronic properties in this flat band I show you, that would be studying a simulation of a triangular lattice Hubbard model, which many of you may be aware is a very interesting quantum system from the point of view of frustrated magnetism and many other. Okay. Let me just okay. So this is the simplest example. There's only one band of electrons, and for each momentum state, there are two states or two valleys, and let me just very quickly mention this second example of TMD semiconductor homobilayers, So here's a model constructed in the same way. Again, it's nearly a universal model. If you assume that the parameters in this model that, or the part of this model that characterizes how the local Hamiltonian is changing as you move in the Moiré superlattice, if you assume that they're smooth functions of position, as they should be because the layers are far apart, then everything is described by only a couple of parameters and depends on no details. This is the case of where you have two semiconductors that are identical, so that means the states at the top of their valence band have the same energy. And so there's a potential energy in one layer, B here is bottom layer, a potential energy in another layer, T is top layer. This is just valence band energy is minus momentum squared going away from the top of the valence band, and the two layers are rotated relative to each other, so their momentum spaces are rotated relative to each other. So the zero momentum in one layer is not zero momentum in the other layer, and so at some places in position, for example, when from what I was saying before, at these yellow points, that means chalcogen in one layer is on top of metal in the other layer, and that means the potential is attractive in one layer and repulsive in the other. And so there's a big difference between these potentials. The color scale here is a map of the difference between the potential in the top layer and the bottom layer. If you regard the layer degree of freedom here as like a spin, then this is an effective Zeeman field, which is couples to this layer pseudospin degree of freedom, and it tells you whether system has more extreme energy in the conduction band or the valence band. Again, it varies by scale of tens of millielectron volts, which is actually very convenient. And the other thing that's plotted here is the tunneling amplitude from one layer to the other, which also varies in position and has a pattern that's dictated mostly by symmetry. Tunneling amplitude, of course, is a complex number, and it's indicated here by these arrows. Length and direction are magnitude and phase of this complex number. And all of this altogether, this pattern in space, is dictated more or less completely by symmetry. And it tells you that the effective magnetic field that acts on this layer degree of freedom has a topological character in position space. When you integrate over position, the effective magnetic field of this Hamiltonian actually covers a full sphere of directions of effective magnetic field, and associated with that, but not in a one-to-one way, it turns out that these bands also have topological character in momentum space. I think you've probably heard a lot in recent years about topological characterization of bands in momentum space. In this case, these are valley projected bands which break time reversal. Symmetry, they're characterized topologically by Chern numbers, the number of times you cover a sphere in some block sphere of one type or another when you integrate over momentum space. And there's a large region of twist angle where these systems are topological in momentum space as well. So that's just to say that in these two-dimensional semiconductors, you can, there's lots of interesting quantum physics to explore in these systems, and this process is just beginning. Okay, so second half of my talk, I'm going to talk about twisted bilayer graphene. Twisted bilayer graphene is similar. It's a little bit more complicated. as I'll explain, just because there's more flavors involved for the electrons. And this is actually a, whoops, I did it again. Okay. This is actually okay, this is actually a slide from one of the I think one of the first papers I wrote when I started to hear about experiments people were doing on these Moiré superlattices, and it actually emphasizes some of the points that I've already been mentioning. So, as you may know, two-dimensional graphene crystals are honeycomb lattices, and in the energy range that's near the Fermi energy, there's only one type of orbital on the carbon atoms that sit on the honeycomb lattice that's relevant. So that means a graphene two-dimensional crystal is described by a one-dimensional, only pi orbital type binding model hopping on a crystal. And people were trying to understand the properties of twisted bilayer graphene systems by making some guesses for how the hopping from pi orbitals in one layer to pi orbitals in the other layer would depend on position. And you can make some guesses for how it should compare if you look up something about tight binding parameters and how people say they depend on position. And actually, in this plot, this is a plot of several different guesses people made, which weren't, as you see, weren't entirely the same. And but it turns out that there's only one parameter, whatever this model is, there's only one parameter that controls how the layers are coupled to each other for states near the Fermi energy. And so in this paper we introduced this quantity. This is just for a tight binding model. And this is a 2D Fourier transform of this pi orbital to pi orbital hopping amplitude. And the point is that if the layers are far apart, this function will always be a rapidly decreasing function of wave vector. So that's one point. And the second point is that the low energy electrons in graphene sheet, and in these semiconductors too, they all have at a certain point in momentum space. And you may remember from looking at electronic structure theory that when you look in a crystal, basically the parameters that appear in the Hamiltonian are just the Fourier transform of how the hopping function depends on position. And so it turns out that that only one parameter, which is the Fourier transform of this hopping amplitude at the smallest possible wave vector, the first harmonic, which is at the corner of the Brouin zone, at least we argued, only this parameter controls the electronic structure. And this is the reason why the atomic scale commensurability issues that we were talking about before simply don't matter when the Moiré period is long. And you never see the incommensurability. And so as I said, in using these kinds of arguments, you could argue that you could describe the electronic structure of the Moiré superlattices in terms of one number. And maybe, and this one number enters in an interesting way, it turns out, if you go through the details, because the graphene lattices are honeycomb lattices, and there are two sublattices of the honeycomb. So when you tunnel from one layer to another, this tunneling amplitude is space-dependent in the Moiré pattern, but it's also sublattice dependent. And so if you go through the details of this model, you get a one-parameter expression for a spatially periodic pattern of the tunneling amplitude from one layer to another, sublattice-dependent tunneling amplitude. I've just plotted here one of these tunneling amplitudes, and which is tunneling between different sublattices. So this is actually a complex number, indicated here by an arrow with magnitude and phase of this complex number. And this is the tunneling between A and B amplitude. And you can see here that when the A atoms of the top layers sit on top of the B atoms, the blue arrows are long. That means there's a large amplitude for tunneling from one layer to another. When the A atom sits on a B atom or another A atom, there's no tunneling from one layer to another. So the spatial, one parameter expression for the sublattice-dependent tunneling amplitude reflects the local symmetries in the Moiré pattern. And you can get a very simple model in this way, a model that is periodic, even though the true microscopic model is not periodic. And so here is the graphene version of the results that come from this kind of Moiré superlattice model for graphene. And let me talk about the right-hand side first. So you can see here this is energy as a function of momentum. This is actually momentum in the what we call the Moiré-Brouin zone, the Brouin zone constructed from the periodicity of the Moiré superlattice. And so this is a good this is a good quantum number in this what we call Moiré band model. And here you can see, if you, for example, look at this point in momentum space, you can see two linearly crossing bands, and those are the linearly crossing bands that we have in individual graphene sheets, so-called Dirac bands that we have in graphene sheets. And at this nearby, slightly different point in momentum space, we also have linearly crossing bands that are localized in the limit of weak interlayer tunneling in the other layer. So one of the things that follows very simply from this simple model, and which is important in understanding the Moiré bands, is that when the twist angle is large, that means the Moiré pattern is short, and the momentum difference between one layer and the other is large. When you scatter from a momentum measured relative to the Dirac point in one layer to the other layer, you get a big momentum boost, and you go to some very different momentum, and that means the energy is very different. And for that reason, when the twist angle is large, the two layers are weakly coupled together. So for example, if you take two graphene sheets and twist them relative to each other by 10 degrees, they hardly know that they're there. Okay? They're basically decoupled at 10-degree twist. When you go to small twists, they start to become coupled. And in this picture, they're starting to become pretty strongly coupled at 2 degrees. And there's actually a Dirac cone in one layer that has an avoided crossing with the Dirac cone in the other layer, somewhere centered around this point at energy momentum space. And you can see here there's a big avoided crossing gap due to tunneling between the two layers. So the layers are starting to be strongly coupled. And whereas you go here at this other point in momentum space, you can see this point I've labeled gamma. There's only a little avoided crossing gap between the two layers. But nevertheless, as you turn the twist angle down, the layers become more and more strongly coupled. And there are layers out to states out to infinite energy relative to the direct, relative to zero energy here in both layers. And so what happens when the level repulsion effect tends to take these states in the middle, near zero energy, and squash them down to zero energy. It's pushing them away from all of the high energy states. And so the magic thing that happens in this system is it turns out that these get states, the blue, which I'll call conduction band, and the red band I'll call the valence band, they get pushed together as the twist angle goes down, and they get pushed together at all momenta at nearly exactly the same twist angle. Okay? And that's the magic property which at a very special twist angle, given in this one parameter theory, if you put in an estimate for this tunneling amplitude, comes out about 1 degree, you get energy that depends nearly, states that are nearly independent of momentum. And that's when we know from our basic knowledge of solid state physics that you get strong correlation effects. So it's important here that we get strong correlation effects not in the limit of very large Moiré patterns, like in the first example I showed you, where the bands just get narrower and narrower the smaller the twist angle, the longer the Moiré period. Here, this flat bands, which will produce strong interaction effects, appear at some intermediate twist angle, some intermediate Moiré pattern length, which is actually very conveniently around 10 nanometers. So in this system, this is sort of an ideal laboratory for studying strong correlation physics because, at least in principle, you can tune how strong the correlations are by just changing the twist angle within about 1/10 of a degree of this 1 degree twist. And the bands are broad, they become narrow, they become broad again. Okay? And you can easily use electrical gates to completely change how many electrons are present in these flat bands. So this is really much better than you could ever do with cold atoms in terms of quantum simulation of a strongly correlated electron system. And so my last few minutes, I'm going to talk about some of the interesting results people have seen, and I should stop in 8 minutes, I guess. Does that sound right? Okay. This subject was given a huge boost by experiments from Pablo Carrillo Herrero, whom you've heard from recently. This is actually, what I'm showing here are some experiments, more recent experiments from the group of Dmitry Yefetov at ICFO in Barcelona. These results are experimental results are showing a richer phase diagram than in the initial experiments. And it's known from various ways of various measurements that the difference between these samples and the original samples is the twist angle is more uniform. I told you these systems are tremendously sensitive to twist angle, so you know you better have a uniform twist angle across your entire device or you're going to have inhomogeneity. So this is the direction for further progress. These samples are not perfectly homogeneous, so there's further progress to be made in making these examples more homogeneous. Along this axis, this is electron density. Importantly, we know that this is the sort of variation of electrical density that you can routinely in every day in Java's lab. You can easily move this number of electrons per square centimeter in and out of any 2D system. And you see in these systems that as you're changing carrier density, you go between these very brown regions are signaling high resistance states. And if you look at the temperature dependence, these are basically insulating states. So what is known, what is suggested from these experiments, although it's not clear maybe for every case, but these insulating states occur at densities that correspond to some integer number of electrons per Moiré period. And they tend to be insulating. Between every insulating state, there's a superconducting dome. The difference in density between this insulator and this superconductor, as indicated by the resistance and the temperature dependence of the resistance, which I'm not showing to you, is a density of about 1 electron for every 10 to the 5th carbon atoms. So this is impressive in terms of what the quality of the samples must be. And the superconducting transition temperatures are bigger than aluminum, so real superconductors.
Alan, I
Go
guess in the
ahead.
first experiment, we had the domes on that side, but not on the whole
Yeah,
side.
so that's just
So holes are more sensitive
inhomogeneity.
like
In
that?
fact, what?
So holes are more sensitive?
Uh,
Or electrons
so
are-
why is
One side is okay, the other one is not. Because if
yeah,
there is an
maybe
inhomogeneity-
we'll understand that in the fullness of time.
Okay.
But there is particle hole asymmetry in the system, and why the biggest difference is that the samples with early samples, and I think we can say the samples with more twist angle inhomogeneity, did not show insulating states at neutrality. In more homogeneous samples, the biggest, strongest insulator at it is neutrality. So one thing I've wondered about is why is this gap at neutrality apparently more sensitive to twist angle disorder than the other ones?
Another quick
So,
question.
yeah.
Do the insulating states occur at half filling of the Moiré lattice?
So they occur at 1/8, 2/8, 3/8, 4/8, 5/8, 6/8, 7/8.
Wow.
Okay, measured of the filling of the flat bands. And it's eighths rather than halves in the case we're used to, because the usual case is electrons only have a spin degree of freedom. Here we have spin and valley, and there are 2 flat bands, conduction and valence. So that's the difference. Yeah, and so there are lots of superconducting domes. And maybe this is just a theoretical extrapolation. Not everything that is indicated in this, whoops, I did it again. This cartoon on the right is actually been seen experimentally, but let me try to, I'm going to skip over these things. I'm just going to try to make one more point. Yeah. Okay, this is another very interesting thing that's seen in these systems. This is again from Yefitov's group, but some closely related measurements had been done by David Goldhaber-Gordon at Stanford. And what this shows is an insulating state. And plotted here is the trajectory of the density at which high resistances are measured as a function of magnetic field. And that shows that the insulating state occurs at a density that depends on magnetic field. And so this shows that the state that we have even here, because as a function of magnetic field, this will go like this. So it breaks time reversal symmetry. And in fact, this is something we kind of understand. And so this is what I showed you. The density at which the insulating state appears depends on magnetic field. And just from some Maxwell's relations, this means that this sample has magnetization. We actually think it's purely orbital magnetization. And And it turns out the dependence of the magnetization on chemical potential is related to the slope of that line, as is the Hall conductivity. So these systems are actually also show a hysteretic anomalous Hall conductivity, a hysteretic Hall conductivity, even without a magnetic field. And I believe this is the first example of something I remember actually asking my professor about when I took a graduate course in solid-state physics, is why are there no orbital ferromagnets? And that's still an interesting question, but this is an orbital ferromagnet. There are no free spins in this system. These graphene sheets are known for having practically no spin-orbit coupling in the micro electron volt scale. And so orbital and spin space break time reversal separately, can break time reversal separately. And in this case, it's orbital space that breaks time reversal symmetry and produces anomalous Hall effect, and we think eventually, as the samples improve, quantum anomalous Hall effect. One of the big questions in this field, of course, is what's producing the superconductivity, and are there any generic lessons we can learn from understanding this? We don't understand it yet, so I can skip over. Fortunately, keep my promise to end on time and skip over this part of the talk, but somebody can ask me about it, and also ask me about some of the things that I haven't had time to mention that are coming along. So thank you very much for your attention.
What causes superconductivity?
Yeah, so,
You said
we don't know. But you know, there is, it could be, as someone mentioned earlier, when you have these Moiré superlattices, the Moiré pattern is actually very sensitive to the motion of one layer relative to the other. And associated with that, it turns out that acoustic phonons have very strong interactions between the electrons in these flat bands and acoustic phonons in the layers. That's a mechanism that has been explored for superconductivity. Graphene also has, of course, very strong interactions between electrons and optical phonons. This is actually a theory we did about trying to understand what interaction of electrons and optical phonons, which are very well understood in these materials, would predict for superconductivity. One of the interesting things is that the normal inequality that we know about phonon-mediated superconductivity, that the phonons are slow compared to the electrons, is flipped here. The graphene optical phonons have an energies of let's say, more than 50 millielectron volts. The bandwidth of these electronic flat bands is around 10 millielectron volt. That means the phonon-mediated attractive interaction between electrons is essentially instantaneous in these systems. And as many of you know, it's the retarded nature of phonon-mediated interactions that makes superconductivity work in many metals, and that's not here. So certainly Coulomb effects and lattice-mediated effects, which are always both present, will compete in a different way here. So I'm optimistic that we're going to be able to understand, maybe just by cultural improvement, we're going to come to a consensus, at least, about what's responsible for superconductivity in this system, but we're certainly not there yet. Yeah.
Thank you.
And just on the experimental side, as I mentioned, it really is, the experimental challenge is twist angle homogeneity to really fully reveal the phenomenology, and I don't think it's been fully revealed yet.
Yes, Paul?
If you stretch rather than twist,
Yeah.
do you get 1D channels?
I think you get. I think you still get a triangular lattice pattern.
But your modulation is in the other direction, right? It's just in one direction. And so you
Yeah.
get close and far, close and far.
The modulations end up also involving the reciprocal lattice vectors of the host 2D crystal. So I think there's no way you can avoid modulation in both directions in these because the underlying lattice is triangular. If the underlying lattice was a square lattice and you just stretched it in one direction, then I think you would get a space dependence that depended only on one coordinate.
What is if the lattice is not the same size, for example, Bn with the graphene?
Say that again?
The lattice constant is not the same for the two layer, like
Yeah.
for example, two materials, for example,
Yeah,
Bn
yeah.
and graphene.
Yeah.
It's going to be
Yeah, so graphene on Bn has a Moiré potential. So it turns out that, just like I said for graphene, if you put graphene on Bn, it makes a Moiré superlattice because the lattice constants differ by about 1%, right? If you twist them relative to each other, then then just like graphene on graphene, it's like they're completely decoupled. So you can turn off and on this effect from interaction with
Is it
with
possible?
Bn.
Okay. Is it possible to see superconductivity or something like that between graphene Bn twisted with small Moiré?
Yeah, so I don't think so. I mean, this magic angle phenomena, by which I mean that the flat bands emerge at a finite twist angle, and the width of the band is a non-monotonic function of twist angle. I think that's a function of having more than one Dirac cone. But people have studied a similar effect, interaction-induced superconductivity, in systems with two graphene layers that are on HBN that's nearly aligned. So the HBN plays a role in that system. And in the fullness of time, I think that all of these degrees of freedom will give us a very nice control knobs for controlling these states. For example, exactly what TC is, or some other property that you're interested in.
So in graphene at high magnetic fields, obviously you have lots of nice fractional or normal quantum Hall and fractional quantum Hall states. If you do it in the twisted version, are you going to see the same, not the exact same phenomena, but the same sort of physical effects for different like composite particles with twisted angles? Like everything will things change much if you have
Yeah, so,
fractional charges?
whoops. So people have studied the effect of a magnetic field out here at large twist angles. And there you get effects that are mostly non-interacting effects associated with so-called Hofstadter butterfly physics, where you combine periodic patterns with Landau quantization. But there are interaction effects, seen out here in a magnetic field that are beyond single particle physics. In this regime, people haven't seen any, the way the interaction effect, the way the interaction effects change in a magnetic field, where is that? Is mostly, so everything is, actually very sensitive to twist angle homogeneity, probably slightly obscured so far. But people have seen these churn insulators I was talking about, sort of are saying we already have a quantum Hall effect even without a magnetic field.
Yeah.
And yeah. So you were going to say?
I'm just thinking a bit more if I just make the simple approximation, say I'm at the 1/3 state or something, so I pretend I'm not in a magnetic field. I just have these different, free particles. Are they going to see the same twist angle and basically realize the same physics, pretending they're not in a field at all?
Yeah, so I think that the magnetic field will change the
That'll
physics.
overcome
Yeah.
everything. Okay.
One of the things that I think there's a very good chance people will really observe is so-called fractional churn insulators that they'll have some analog of the fractional quantum Hall effect, even without a magnetic field. Yeah.
I guess continuing on that, if I go to a composite fermion 1/2, then you have a Fermi seed. Do you see the twist interaction and all that? And can you open up phases like this?
Well, I have to start by admitting I'm a heretic about composite fermions.
Okay.
But yeah, so composite fermion is an idea for that helps describe the fractional quantum Hall effect for electrons without a periodic potential. I think those ideas will just fall apart when you add a periodic potential. It's not a good way of thinking about it. That would be my guess.
Okay, so please join us for a reception on the 8th floor, and let's thank Allan for a very